Imagine riding a bicycle down the side of a jagged Chilean volcano.
Oh boy.
Yeah, and you are not coasting, you are plummeting. Like picking up speed until you hit exactly 167.6 kilometers per hour on a bicycle.
It sounds impossible, but that is not some hypothetical physics problem.
No, it's not. That is a very real record set by Marcus Stokel. So, we're looking at a sport today where gravity isn't just a force, it is simultaneously the engine powering you and the absolute enemy trying to destroy you.
Which is such a wild dynamic.
It really is. So welcome to today's deep dive. We are so glad you are joining us because today we are taking you to the absolute terrifying limits of human physiology and engineering, all in the world of extreme mountain biking.
Yeah, it's an incredible subject because what we're really exploring today isn't just extreme sports. This is, a fascinating look into human neurobiology, biomechanics, and really just how evolutionary reflexes are being pushed to the absolute edge.
Right.
We are looking at athletes who are fundamentally hacking their own biology to survive.
Right. Okay, let's unpack this. Because to really grasp how a human being survives a 167 kilometer per hour descent or, an 80 kilometer per hour run through pure rock gardens, we kind of have to look at the machinery first.
We do. And the origins of that machinery are wonderfully, almost comically reckless.
So reckless. If we look back to the 1970s in Marin County, California, you had these pioneers like Gary Fisher and Joe Breeze, and they weren't riding high-tech carbon fiber.
Not at all.
They were riding old 1930s delivery bikes, just these heavy steel frames. They literally called them clunkers.
Which is just the perfect name, honestly.
Right.
And, the defining feature of these early rides was the famous repack race down Mount Tamalpais.
Right.
It wasn't just a race of speed. It was really a race against mechanical failure.
Because actual mountain bike geometry and technology, it just didn't exist yet. They were bombing down these mountains using coaster brakes. You know, the kind where you pedal backward to stop like on a kid's bike?
Exactly.
I cannot even imagine the sheer terror of relying on a coaster bike on the edge of a cliff.
Well, the physics of it are what makes the history so important. Because a coaster brake stops the bike via internal friction. And since they were going down a literal mountain, the friction heat from braking was so intense that it would literally melt the grease right out of the hubs.
That's insane.
Yeah. When they got to the bottom, their brakes were entirely burned out. So they would physically have to open up the hubs and repack them with fresh grease. Hence the name, repack race.
That makes so much sense.
Right. This mechanical bottleneck, the fact that traditional bike parts literally melted under the forces of mountain gravity, it forced the invention of the modern downhill machine.
And the evolution from melting grease to what they ride today is just staggering. I mean, it's basically like taking a wooden soapbox derby car and trying to upgrade it into a supersonic jet without adding an engine.
That is a great way to put it. A modern downhill mountain bike is essentially a gravity-powered Formula One car. The engineering is entirely focused on managing violent physics.
So what does that actually look like?
We'll take the frame geometry. They use a 63-degree head angle.
Yep.
If you picture a standard road bike, the front fork goes almost straight down. A 63-degree slack angle pushes the front wheel way out in front of the rider, almost like a motorcycle chopper.
Wait, so it's kicked way out. So when you hit a boulder at 60 kilometers an hour, it acts like a battering ram rather than a catapult launching you over the handlebars?
Precisely. It provides this essential stability. And to keep the tires actually touching the ground over those boulders, you have 200 millimeters of suspension travel in both the front and the rear.
Wow.
That's about 8 inches of pure, tunable shock absorption.
And to stop this machine, they've thankfully moved past coaster brakes, right?
Yes.
They use these massive 200 to 220 millimeter steel rotors with 4 piston hydraulic brakes, which is literally motorcycle braking power. Plus, they use this specialized tire setup called the mullet.
Business in the front, party in the back.
Exactly. A massive 29-inch wheel in the front to just steamroll over rocks, and a slightly smaller 27.5-inch wheel in the back to keep the rear of the bike agile enough to whip around tight corners.
It really is a masterpiece of specialized engineering. But a machine like that only exists because of the arenas where it's tested.
Right.
Mountain biking has several disciplines. You have cross-country, which is agonizing physiological endurance over long distances. You have enduro, which times the descents but forces riders to physically pedal back up the mountain.
Ugh, brutal.
Yeah. But then you have the 3 phases of pure gravity: downhill racing, free ride, and urban downhill.
The terrifying 3. Because in a World Cup downhill race, the average speed is 40 kilometers per hour, but they were hitting peaks of 80 kilometers per hour.
And that's over wet routes, jagged rocks, and massive drops.
Yeah. The tracks are legendary. You have Whistler in Canada, which is the global mecca, the Port du Soleil in Europe, Fort William in Scotland, which is notoriously long and physically brutal, and then there's Val di Sole in Italy.
The Val di Sole is infamous. It features a track called the Black Snake. It is widely considered the steepest, most technical, and most unforgiving track on the planet.
Just a total nightmare.
It is an absolute gauntlet on a near-vertical pitch.
And if mountains aren't enough, you have urban downhill. Races like Cerro Abajo in Valparaiso, Chile, where riders navigate unpredictable city streets, literally flying down narrow concrete stairs, jumping over retaining walls, and dodging stray dogs.
It's pure chaos.
It is. But here's the thing. Even a bike engineered like a Formula One car has a fatal flaw. It still relies on human hands to steer it. Which brings me to a massive question for you. Wait, if they are hitting these rock gardens at 80 kilometers per hour, how does the human skeleton not just vibrate apart into a million pieces?
That is the crucial question. And the answer is that the bike's 200 millimeters of suspension is only half the equation.
Okay.
The human body has to perform literal physiological miracles to survive the ride. The research done by sports medicine specialists, specifically Dr. Christophe Delong, sheds incredible light on this.
Oh, I've read some of his stuff.
Yeah, he's analyzed the sheer muscular demand of extreme sports. And what's fascinating here is how the rider's body must transform into an active biological suspension system.
Because it's a completely different physical demand than, say, pedaling a road bike on asphalt.
Entirely different. Road biking is a cyclic effort. It's a continuous rhythmic spinning. Downhill racing is an acyclic effort.
Got it.
The rider is standing up on the pedals the entire time. Their legs, specifically the quadriceps and glutes, are locked in an intense isometric contraction.
An isometric contraction, meaning the muscles are firing at absolute maximum output, but the joint angle isn't changing. So it's kind of like doing a wall sit, but holding that wall sit while someone hits the wall with a sledgehammer.
That is a brilliant way to picture it. And those sledgehammer hits are what sports medicine calls eccentric shocks. Every single rock and route is sending violent upward force through the pedals, trying to force the rider's legs to collapse.
Yike.
So the muscles have to absorb that energy while maintaining their static position.
And they are holding this position for 3 to 5 minutes straight. Your muscles have to be absolutely screaming, starved for oxygen, flooding with lactic acid. But you can't give in for a single millisecond.
Right. And while the muscles are burning, the biomechanics have to be flawless. They use a technique called heels down.
What's that?
By physically dropping their heels below the pedal axle, they dramatically lower their center of gravity. It changes the physics of an impact. Without dropping the heels, hitting a rock throws your mass forward right over the bars.
Which is exactly what you don't want.
Exactly. With heels down, that forward momentum is driven down into the bottom bracket of the bike, driving the tires harder into the dirt.
So you essentially wedge yourself into the machine, and the visual of this is eerie. If you watch a pro rider in slow motion, the bike is pitching forward, rolling side to side, bouncing violently, but their torso stays perfectly still.
It's wild to watch.
They completely dissociate their upper body from the chaos happening beneath their feet.
It's extreme body isolation. But guiding all of this muscular control is an even more extreme neurological demand, starting with vision. If you strap a camera to the bike frame at 80 kilometers per hour, the footage is just a blurry, unwatchable mess. But the rider uses a vestibulo-ocular reflex to stabilize their vision.
Which is the inner ear communicating with the eye muscles.
Exactly. The fluid in the inner ear detects the exact angle and speed of the skull's vibration and fires a signal to the eye muscles to move in the exact opposite direction in real time.
Oh, wow.
Yeah, it keeps their visual target perfectly locked despite the skull vibrating violently.
And vision dictates everything. It's a chain reaction. The eyes lock onto the exit of the corner. The head turns to follow the eyes. The shoulders drop to follow the head. The pelvis shifts. And finally, the bike follows the body. The vision literally pulls the entire machine through the obstacle.
But, vision only works when everything goes according to plan. And in mountain biking, the terrain is constantly shifting. Wet dirt, loose rocks.
Okay, let's unpack this, because this is exactly what I was trying to wrap my head around. If a wet route suddenly kicks the front tire sideways at highway speeds, waiting for a visual signal to reach the brain, be processed, and send a movement command back to the arms, I mean, you are already wrapped around a tree by then.
Oh, easily.
So how are they physically making the correction in time?
If they wait to consciously react, they've already crashed. You're entirely right. Human nerve conduction simply isn't fast enough. So the brains of elite riders utilize a predictive engine called a forward model. They don't wait for the slip to happen.
So what does this all mean?
It means their cerebellum is constantly comparing the intended motor command, where they want the bike to go, with the tactile reality of the terrain. The brain basically acts like a biological time machine.
That is crazy.
Yeah. Before a slide is even consciously perceptible, the cerebellum has already pre-activated the antagonist muscles to counter it.
But wait, how does the body detect that microscopic start of a slide if the eyes haven't even registered it yet?
Through a highly advanced biological detection system. Mechanoreceptors in the skin of their hands and feet detect microscopic changes in vibration.
Okay.
If the tire loses traction, the vibration frequency changes instantly. Simultaneously, the inner ear detects the sudden lateral acceleration. All of this data hits the spinal cord in milliseconds.
And it bypasses the conscious brain entirely.
Entirely. The counter-steering happens via a spinal reflex arc. The statistics on this, measured by biomechanics labs, are just mind-bending. When a rider is navigating a slippery off-camber corner, their outside leg is making 10 to 15 microcorrections per second on the pedal.
Wait, 10 to 15 conscious shifts in weight per second.
Subconscious shifts, just subtly altering pressure, hunting for the exact microscopic bite point of the rubber against the dirt.
That is superhuman. But all of this microcorrection relies entirely on the rider's physical connection to the machine, the hands.
Yes.
Which leads to what is probably the most fascinating physiological paradox of the sport.
The grip paradox. When you are going over a rock garden, you have to grip the handlebars firmly enough to actively steer and force a 25-pound bike exactly where you want it.
Right.
But you must be supple enough to absorb the impacts without letting the vibrations tear your hands off the grips.
If you've ever gripped your steering wheel too tight during a close call on the highway, you know that rigid tension. Now imagine holding that tension while your hands are being hit by a jackhammer.
Exactly. And to manage this, riders have to fundamentally rewire their motor control. Teams like Kinexa, who specialize in movement biomechanics, have actually studied how these athletes utilize finger dissociation.
Right, because normally if you grip something tightly, your brain uses a map called the motor homunculus. And in that map, your fingers are essentially wired to work as a linked unit.
They want to clench together.
Yeah. Try squeezing your bottom 3 fingers as hard as you can while keeping your index finger completely relaxed. It's incredibly difficult.
It defies our natural biology. But these riders train their nervous system to separate the index finger from the rest of the hand.
Wow.
The index finger rests lightly on the brake lever, modulating hydraulic pressure with the delicate sensitivity of a surgeon. Meanwhile, the middle, ring, and pinky fingers are clamped around the bar with the strength of a vice.
And while the hands are doing that impossible split task, the arms are performing what Dr. Delong and other specialists refer to as impedance control.
Yes, the triceps and biceps co-contract. They become living hydraulic dampers. The brain is constantly adjusting the stiffness of the arms.
So they aren't just rigid the whole time.
No. When rolling over small rocks, the arms are loose, filtering out high-frequency vibrations. But the millisecond before hitting a massive drop, the arms instantly stiffen to resist the low-frequency massive impact.
But human anatomy has a hard limit. And this brings us to the ultimate enemy of the gravity athlete, which is arm pump.
Arm pump is the physiological failure of this entire impedance control system. Because the forearms are locked in that intense, constant contraction to hold onto the bars, the muscle fibers swell, and they act like a tourniquet.
Here's where it gets really interesting. Arm pump is basically a one-way vascular traffic jam. The entrance ramp is wide open, but the exit is completely bricked off.
That's exactly the mechanism. The heart is pounding, pumping arterial blood into the forearms at maximum pressure to feed those working muscles. But the constant, rigid contraction of the forearm muscles squeezes the veins shut.
Oh, I see.
Veins have much lower pressure than arteries, so the deoxygenated blood cannot get out. The forearms literally swell up, doubling in size, and turn as hard as stone.
And once that happens, the mechanics fail completely. The pressure in the forearm compresses the nerves. You lose the tactile ability to feel the handlebars. Your index finger loses the strength to pull the brake, and the burning pain is agonizing.
But the elite riders have developed a hack for this. It's terrifying, but brilliant.
What do?
While they are launching off a massive jump, hovering 15 feet in the air, they will micro-release their grip on the handlebars for a fraction of a second. They just open their hands slightly.
Midair.
Yes. This brief release creates a lightning-fast blood flush, allowing the trapped venous blood to escape before they clamp back down for the landing.
So they are managing their vascular pressure in midair, and they are doing all of this while their nervous system is actively performing sensory gating.
Right.
It's like when you get a deep cut but don't feel it until you actually look at it. The brain physically gates off the pain signals from the hands and arms because the processing power is entirely focused on the front wheel's traction.
But inevitably, when the arm pump wins or the motor processy fails, well, gravity collects its toll. When you are pushing the limits of physics, crashing isn't just a possibility, it is a statistical guarantee.
Yeah, that's just the reality.
Which brings us to the ultimate cost and the anatomy of a champion.
And we really see this cost scale differently across the two main branches of the sport. You have UCI World Cup racing and freeride.
Right. The World Cup is a timed race. It is a millimeter-precise hunt for hundredths of a second. Athletes like Loic Bruni and Amaury Pierron tune their bike suspensions to keep the tires glued to the ground at all times. Because in a race, airtime is slow time.
Right. You can't accelerate if your tires aren't touching dirt.
Exactly.
But then you look at freeride events like the Red Bull Rampage. This is the extreme figure skating of the sport. There is no clock. Riders are judged on the sheer terror, technicality, and artistry of their lines.
It's a completely different beast.
They aren't racing down an established track. They are building their own narrow paths down near vertical, loose sandstone cliffs in Utah.
And their bike setup completely changes. The suspension is incredibly stiff to survive drops that would literally snap a normal bike frame in half.
We're talking about dropping 20 meters off a cliff, which is a 6-story building, and doing backflips and 360s in the middle of the danger. It requires the mindset of a stuntman combined with an artist, and very rarely do these worlds cross. Brandon Semenuk is one of the rare crossover talents who started in racing and then completely dominated freeride.
But regardless of whether you're trying to shave a tenth of a second off a clock or land a backflip off a 6-story cliff, the grim statistics apply to everyone.
And these numbers are incredibly heavy. 90% of riders will suffer a broken collarbone. It is literally the signature rite of passage.
And 100% will face concussions. That is the invisible plague of the sport. In freeride, the danger isn't just horizontal speed, it's vertical gravity. When your average drop height is 20 meters, you have zero margin for error.
And that brings us to the big one. The massive, career-threatening crash. Every rider has one.
Sadly, yes.
What separates a highly skilled amateur from a world champion is the psychological and neurological resilience required to face that trauma. We are talking about athletes like Miriam Nicole, Amaury Pierron, and G. Atherton. They have suffered punctured lungs, shattered vertebrae, shattered femurs.
They go through months of intense physiological healing. But the defining factor of a champion is that after all that trauma, they return to the start gate and they drop in without losing a fraction of their speed.
Which is the part I struggle to comprehend. Like, how is that neurologically possible? If your brain remembers exactly the agonizing pain of shattering a femur in a rock garden, how does it allow you to ride into that exact same rock garden at 80 kilometers per hour? Survival instinct should literally force you to hit the brakes.
It absolutely should. And for a normal person, it would. But these athletes access a deeply trained flow state. In this state, the prefrontal cortex, the part of the brain responsible for conscious thought, anxiety, future planning, and fear, essentially shuts down.
It just turns off.
Yeah, it experiences what neuroscientists call transient hypofrontality.
So they aren't suppressing the fear, they are literally turning off the part of the brain that generates the fear.
Exactly. They hand complete control over to the primitive, highly trained structures of the brain, like the basal ganglia and the cerebellum. And physiologically, they rely on a highly regulated release of endogenous opiates, the body's natural painkillers like endorphins, to manage the chronic pain of their past injuries and the massive impacts of their current run.
They are essentially biohacking their own trauma response.
If we connect this to the bigger picture, sports medicine experts analyzing these athletes have realized that a champion downhill rider is essentially a positive biological aberration.
A positive biological aberration. I love that.
They possess a motor library of thousands of hours of ingrained muscle memory. They have a nervous system that processes optical flow faster than a normal human, muscles that act as living hydraulic dampers, and an uncanny ability to completely compartmentalize mortal fear and transmute it into laser-focused performance.
It is just sheer awe. When we look back at where we started, Gary Fisher melting the grease out of old delivery bikes on a fire road in the 70s and compare it to today, We are looking at super athletes flying down vertical rock faces on engineering marvels.
It's unbelievable.
They are filtering 80-kilometer-per-hour vibrations through their cerebellum, managing tourniquet-level vascular pressure in their arms in midair, and shutting down their prefrontal cortex just to survive the ride.
Okay.
It fundamentally changes how you look at what the human body is capable of adapting to.
It really does. And I think it leaves us with something profound to consider. If these athletes can literally rewire their nervous systems to perform under that level of extreme physical threat, if they can transform sheer mortal terror into a perfect predictive flow state, well, it raises an important question.
Which is,
How much untapped potential do you have to neurologically repack your own string responses in your everyday life? If the human brain can learn to relax its index finger while the hand is holding on for dear life over a cliff, what kind of psychological grip could you learn to loosen?
that is an incredible thought to leave on. Thank you so much for joining us on this deep dive into the absolute limits of gravity, engineering, and human biology. We hope this gave you a whole new perspective the next time you see a mountain, or even just a bicycle. Keep learning, stay curious, and we will catch you on the next one.